right, good morning everyone. So welcome to my talk on simplifying stepwise explanation sequences. My name is Ignace, and this is joint work with Emilio, Bart, and my promoter Tias as well. And this was presented at the CP conference in 2023. So I'll start with a short overview of the presentation, just to give a feel of what's coming, and then I'll get right into the first point. So let's say you are tasked with modeling some use case related to manufacturing, right? So you have some constraints about the physical equipment, for example, which you try to model, and you try to maximize or minimize some objective functions. So for example, try to minimize the costs or maximize the profit, for example. And so what you do is you put all of these constraints into your favorite modeling languages. In this case, I used CP2023, and then you write a very nice model, right? And once that's modeled, you can give it to any solver, and then hopefully your solver will come up with a nice solution for your problem. So that's very nice. But as probably many of you have already experienced at some point, the first iteration of your model will likely look something like this, right? There's no solution to your problem, so it's unsatisfiable. And this can have many causes. Maybe you have made a mistake in your model, or it's inherently unsatisfiable, that it's just physically impossible, for example. But in any case, you would like to know why it's unsatisfiable, right? Why there's no solution found. And how to do that? Well, there is this thing called a MUS, which is a minimal unsatisfiable subset of constraints. And what this will do is it will find a set of constraints that makes your problem unsatisfiable, right? So it will pinpoint the constraints that are the cause of one of the conflicts in your problem. And you can use, for example, the MUS tool in CP2023, and Minisync as a similar tool as well. So that's very nice. But the problem with this MUS is, well, in some cases, there may be many constraints involved in the conflict. In the extreme case, even all of the constraints in your problem. So then extracting a MUS doesn't really help in understanding why something is unsatisfiable. But nevertheless, we would really like to be able to explain why a model has no solution. So the first application that I showed is, well, it helps in debugging your model, but it also has many other applications. So for example, explaining the optimal objective value can be caused to explaining unsatisfiability by making sure, or by trying to explain why there's no better solution. But also in other applications, such as interactive configuration, where a user maybe tries to build a solution in collaboration with a solver, for example, and he picks some part of the solution that are incompatible. Well, then we would like to explain to the user why this is incompatible. And yeah, there are many more applications of explaining why something is unset. So we would really like to do that. And the way we propose to do that is by using ideas from stepwise explanations. So instead of going for a MUS, we will go for stepwise explanations. So what are these stepwise explanations? Well, a stepwise explanation is a sequence of small explanation steps in which each step derives a set of literals using previously derived literals from other steps and some constraints. So may sound a little abstract, but let me give you an example. So for example, in the Sudoku case, here you would use as input literals of this step some of the given facts in your Sudoku, or some of the filled in cells, and then you will use this this row constraint and this column constraint to derive, well, in this particular cell should be a 2. And then, of course, in the, some next step, you can reuse the fact that this cell is a 2 to derive new things, etc. And you can repeat this a lot until your full solution is actually found. So this has been very well studied already, but mainly in the context of explaining the full unique solution of a problem. So for example, Sudoku or other logic puzzles. So this is important because this means that there's no redundancy in the sequences, while in other use cases, this might be the case. So this was the main insight that we got from applying stepwise explanations to arbitrary goals, like for example, explaining unsatisfiability, that we have some risk on redundancy in the sequence. So we came up with some properties that would characterize this redundancy, and that we would like good sequences to adhere to. And we also proposed an algorithm stack or an approach to actually find these sequences that adhere to these properties. And so the remainder of the presentation, it will focus on explaining unset, but it can be applied more general as well to explain other sets of output rules besides just the conflict of a set of unsatisfiable constraints. So let me give an example of stepwise explaining unset or stepwise explaining optimality in this case. So I will use the shortest path problem for this. So let's say you have a graph where you want to find an optimal path from your start node S to a goal node G. Well, then we add a constraint that we should at some point leave S, and we should at some point enter G. So the decision variables are a Boolean, whether we take an edge or we don't. And then these constraints are called flow preserving constraints, which basically means that if you enter a node, then you should also leave it as well, and vice versa. And of course, we have an objective function. In this case, we try to minimize the weight of the path that we found by using the weights of these edges. And so in this case, the optimal solution or the optimal path has a cost of 4. So if we now add the constraint, well, I want to find a solution that's less than 4, then this will be unsatisfiable. There will be no solution, of course, because 4 was optimal in the first place. So how to derive or how to explain why there's no solution with a cost of less than 4? Well, we can use stepwise explanations for this, right? So let's start this. So by using the constraint that we should have a total weight of less than 4, and the fact that if we leave C, we should also enter C at some point, so we should use one of these two edges, then we can derive, well, this will always exceed the total allowed weight of our path, so this edge can actually never be taken, right? And if we know that edge can never be taken, and we know that we should at some point enter G, then we can derive, well, then we need the edge D to G, right? And we can continue this. So if we know that we leave D, then that means we also have to enter D at some point, right? And if we know that we use this edge of a cost 1, and we know that the total cost of our path should be less than 4, well, that means that we can never use this edge in combination with the one that we already chose, because it would exceed the total cost. So we can never use S to B. And let's continue. So if we leave B here, right? So we use this edge, and we do not use this edge. Well, that means somehow we have to enter B, which in this case would be A to B, right? And then if we know that we have a subpath of size 3, of cost 3 already, sorry, well, that means that we can never actually use this edge because we already are at full capacity, let's say, for a solution. So we can never use this edge S to A either. And so now, of course, you already see there's a problem. We cannot use S to A and also not S to B, but we have to leave S. We have to start our path at some point. So there's no solution for this last part. So now we decomposed, let's say, the explanation into small steps that we can easily follow along, instead of just presenting some constraints, right? But I said, well, there's redundancy or risk of redundancy in sequences when you try to explain unset, right? So what do I mean by that? Well, let's go back to the very first step we had, where we derived that C to G could not be used, right? Well, I said this is because we don't actually, or we can't take any of these two edges in combination with this one, right? But we didn't derive that we cannot use either of these. So why did we not derive it? Well, because we never use it later on in the explanation sequence. And so this is, for example, a nice example of redundant output literals that we could have derived that A to C is not used and B to C is not used. From the same set of constraints that we derived C to G is not used. But we didn't do it because, well, we actually don't need it for our explanation. So this is very important. So what exactly are these good sequences, right? How to characterize good sequences, or how would we like good sequences to look? So we have derived 5 main properties. So first of all, we say that the steps, should be atomic. And that means that steps contain as little constraints as strictly needed. So this helps, of course, in understanding individual steps. Second, we say that steps need to be sparse. They use as few input literals as needed to derive what they need to derive the output literals of that step. But then, of course, which output literals to derive. That's dependent on, well, one, the goal that we try to explain, but also what literals later steps need as well. So we say a sequence should be pertinent. So that means that all of the output literals of a step should be reused later or be part of the goal that we try to explain. And then lastly, we also say that, well, all steps should actually serve a purpose, right? So if a step has none of its output literals reused as input later, then it's clearly not needed. And if a step derives output literals that could also be derived by other steps, maybe by multiple other steps, without altering their constraints, then we say it's redundant. We could have left that step out and just let other steps derive the output literals as well. So these are the 5 properties that we came up with that we believe are good or are good for good explanation sequences or easy to understand explanation sequences. So how exactly can we make such sequences? How can we construct these? So we propose a 3-phase approach in which, first of all, we have a greedy construction phase. So we just try to find a sequence to our goal. Then we will filter out the redundant steps from the sequence. And then lastly, once we have a shorter sequence, we can actually remove the input and output literals that are not needed to explain our goal. And I'll show you in detail how we exactly do that. So first phase, construction of a sequence. So to find a new step, we enumerate subset of constraints in the order of size. So we start with size 1, then size 2, etc. And for each subset, we try to maximally propagate all of the constraints in that subset in combination with all of the literals that previous steps have already derived, right? So if a new literal is derived from using these constraints and all of the input literals, then that means that something is derivable here, and we add the step to the sequence. And we repeat this until our goal is derived, and this will always finish. And this approach, it results in maximal sequences, and maximal sequence is a normal form that we've defined for sequences, and they mean, or it means that a step has as much input and output literals as possible. So it uses all of the input literals, or all of the literals that are derived by previous steps, and it derives as many new literals that are possible by maximally propagating that set of constraints and derived literals. And this ensures that our steps are atomic, that they use as little constraints as needed to derive whatever they need to derive. And this is, of course, because we enumerate the constraints in order of size. So once we have this sequence, it may contain useless steps, right? It may contain redundant steps. So how can we fix this? Well, for each step in a sequence, we check if we take out that step, do we still have a valid explanation sequence? And by valid, I mean if I now recompute each of the steps, can I still derive my goal that I want to explain? So this is very expensive, right? Because we need to compute each remaining step, but it will ensure that we don't have any redundant steps in our resulting sequence. And I will show you later also in experiments that this is definitely a needed ingredient in our approach. And we call this deletion-based filtering because, well, it tries to delete steps. So once we have our shortened sequence, this will still be maximal, right? So it will contain many input and output literals, namely as many as possible. And this is not very easy to understand for a user. So in the last step, we try to prune away the unnecessary input and output literals. So how we do that is we start from back to front. So we keep the output literals that are needed, namely the output literals that are used in later steps. And then we only keep the input literals that are needed to derive those required output literals. And so this can be run after deletion-based filtering, like I've done now. But you can also do this without deletion-based filtering. And this will remove loose steps. So at some point it may be that some step does not have any useful output literal, and then of course you can remove this. But this will not be the case if you do it after deletion-based filtering, as all of the loose and redundant steps will already be gone. So this approach ensures that the steps are sparse, so they have as little input literals as possible, and they also are pertinent, so they contain as little output literals as strictly needed because of the first part, of course. And this is called relaxation-based filtering, as we try to relax the step in some way. So let me quickly show how this would work for our shortest path problem. So if we try to clean the input and output of this particular step, so let's say we have these two edges that have some value, so we don't use C to G and we use D to G. Well, to derive the fact that we need B to D, we don't need the fact that C to G is not chosen, right? We only need this one. So in this case, we will remove C to G not equal to 1 from our step. And this can be done by computing a mus at a sublevel, but it would take a bit too much time, I think, to go into detail on how exactly we do this. So on to the results. So I said, well, it's very important to do this deletion-based filtering to remove these redundant steps. and that you can clearly see here, right? So if we start from our normal form, we have about 120 steps for for an explanation sequence of explaining the optimality of a job shop model. And if we remove all of the redundant steps from that sequence, we have about, I think it's 37 steps on average. So that's of course a huge reduction and a lot less to consider for a user. And this is also very interesting. Relaxation-based filtering, so this is if we don't apply deletion-based filtering, but just do the relaxation-based and remove any step that's loose after this relaxation, then we still can remove a lot of the redundant steps. Then onto the individual steps themselves. So how complicated is a step, let's say, in terms of input and output? So if you just relax, we get on average about 17 input literals for each step. But interestingly, if we first do deletion and then relaxation, like I've shown in the approach before, then actually we get more difficult steps, right? This is logical. You have less steps, as we have seen before. You have less steps using deletion, but of course the steps themselves will get a bit more complicated. And this is the case for both the input and the output literals for each step. So there is a bit of a trade-off between the two, less steps or more complicated steps in terms of input and output. So why is this interesting to run only relaxation? Well, because it's a lot faster. So what I said, deletion-based filtering, it's you have to recompute each remaining step, so that's very expensive. While if you just do relaxation, it's much faster, and you can still remove a lot of the redundancy in your sequence. And so you can clearly see that from this plot here as well. So to conclude, we think that stepwise explanations can definitely be applied to explaining unset CSPs, but we do require a lot of extra care to avoid these redundancies that we talked about. So as a quick reminder, we have 3 phases which are able to get rid of this redundancy, both in terms of full steps and also input and output literals. And this was shown in the experiment that this is very worthwhile to do. So this is of course not the end of the story. We can improve this approach a lot, I think, by, for example, dealing with redundancy in the construction phase already. We have now a very greedy approach, but we can do this a bit more, a bit smarter, I think, especially if we combine this with some heuristic approaches to guide the construction a bit instead of just blindly adding steps in arbitrary order. And also in terms of post-processing, I think you can make the sequences even more comprehensible by altering the constraints or swapping steps, for example. This may be worthwhile to do to make the explanation a bit more precise or clear for a user.